Okay, we'll start with number 1. Okay, so this is Chapter 5, recovery, health session number 1. Okay, it says let the function defined by negative natural log of x over x. Half the work is already done here. It tells us that f prime is equal to 1 minus 2 natural log of x over x cubed. So we just have to find points of inflection. We have to move from f prime to f double prime. So we're just starting at f prime level here. Okay, so to move to the second derivative, we have to go through quotient rule. Derivative of f1 goes to 0. 2 natural log of x becomes negative 2 over x. The original g function. Back to f. And then g prime. All over denominator squared. All right, so now we just want to do a little bit of cleanup. Good so far? Okay, so this becomes negative 2 over x times x cubed. One of the x's goes away. We're left with just negative 2x squared. Distribute the negative 3x squared through the parentheses. Negative 3x squared times negative 2 natural log of x becomes positive 6x squared natural log of x. All over x to the 6th. All right, continue cleaning up. Take out a GCF of x squared. Okay, I can take x squared away from numerator and denominator. So there's our cleaned up second derivative function. Okay, we want to find our critical points. We set the numerator equal to 0. And we can try to set the denominator equal to 0, but if we set the denominator equal to 0, x equals 0, and we know that 0 is not part of our domain because natural law can't take 0 to begin with. So just the numerator. Natural log of x equals 5/6. Add the 5, divide by 6. I want to solve for x. X is stuck inside natural log, so we want to involve its inverse so that that natural log can be taken out. We raise both sides with e as the base. Okay, so that's our critical point. We're going to place that onto our second derivative sign line. We already know that 0 is going to be a starting point because natural log can't take anything less than 0. So now we just want to pick values on either side of e to the 5/6. We want to take advantage of the fact that it's easier to evaluate if everything's in terms of e. So less than 5/6 could be maybe e to the 1/2. Because 1/2 is less than 5/6. And anything, I could do e to the first or e to the second. Okay, we can test it against the second derivative function. -5 plus 6 natural log of e to the 1/2 over e to the 1/2 to the 4th. Really don't care about the value, just want to know what the sign is. So if I brought that 1/2 down, that becomes 6 times 1/2, which is 3. Natural log goes away. 3 minus 5 is negative. So concave down. Plug e squared in. Bring the 2 down. 2 times 6 is 12. 12 minus 5 is 7. 7 over e to the 6th. That's positive. So concave up. There's a change in sign. So therefore, point of inflection. Okay, so we're going to insert our x value back into the original function. Leaving it in this form is fine, but we can bring that 5/6 down. The negative will just stay with it. So -5 over 6 e to the 5/6. Okay, questions, Caitlin? Good. Okay. All right, number 2. Okay, number 2, position of the particle moving along the axis given by x of t. So it says find v of t. Okay, so we want to go from position to velocity. We have to go through derivative. So hopefully we can recognize the fact that there are 2 distinct terms here, separated by the parentheses. So we're going to go through product rule. F prime g plus f g prime. E to the t becomes just e to the t. F stays. Back to f g prime. do a little bit of cleanup here. I can factor an e to the t out from both of these terms. Makes it easier for me to merge some of these together here. All right, I'm just looking to speed things up a bit. I got two terms, common factor I can pull out. Okay, we'll come back to this. Part B, find a of t, acceleration. So we go through product rule again. Factor e to the t out. You can leave it in this form, that's fine. Factor e to the t out. Do a little bit of cleanup here. Part C says, for what values of t is the particle moving to the right? So we want to create a velocity sign line. But first, we want to set our velocity equal to 0. So do a little bit of cleanup here. Factor a -3 out. Leaves me with t squared plus 2t minus 3. I rearranged this so I can go through some factoring here. Set velocity equal to 0. Nothing from here. E to the t is never 0. It's just these two critical points. So t equals -3 and t equals 1. Direction says for all real numbers. So we're going to include -1 in our sign line. Okay, choose values on either side. I'll choose -4, I'll choose 0, and I'll choose 2. Back to the velocity function here. Negative, negative, negative. So 3 negatives. Plug 0 in. Negative, positive, negative. 2 negatives gives me positive. Plug 2 in. Negative, positive, positive. So moving right would be where we have positives going on here. So moving right. From -3 to 1, because velocity is greater than 0. Okay, is the velocity of the particle increasing or decreasing? So velocity increasing or decreasing is purely relying on just acceleration. So at 0, we can plug 0 into the acceleration function. I get 0, 0 plus 3, 3 times e to the 0, that's a positive. So because acceleration of 0 is positive, we know that velocity is increasing. Go with that. All right, number 3. Find dy dx for log base 7. This may look daunting with that base 7, but pretend like the problem was just natural log of a over b. All right, we'll do the same thing that we did if we see natural log of a over b, we would expand. We want to take advantage of expansion properties, otherwise u prime over u is just too messy to work with. Keep expanding, bring that exponent down. All right, we wrote that 4th root as raised to the 1/4. Keep in mind the derivative for log base a of u is 1 over natural log of a times u prime over u. All right, it's basically u prime over u, just with a little bit of adjustment with the fact that it's log base 7 and not log base e. So 1 over natural log of 7 times u prime over u. Minus coefficient 1 over natural log of 7, and then u prime over u. Can rewrite it a little bit cleaned up if you like, but either's fine. Good, Kaylin? Okay. All right, number 4. dy dx. Okay, so 3 things we have to take care of. We want to take care of expansion, and then we got to deal with implicit because of y's all over the place, and then there's a product rule that's hiding right here as well. Okay, expand first. Keep expanding. Rewrite this as y to the 1/2. And if you have it written as natural log of y to the 1/2, you can push that 1/2 down in front, get it fully expanded. Okay, so now we can apply our derivative rules. Natural log of u becomes u prime over u with dy dx. There's no y's here, so just u prime over u. Product rule here. F prime times g, F g prime. 2y becomes 2 dy dx. And then 14 goes to 0. Okay, so we want to rearrange. We want all the dy dx terms together. Factor out the dy dx. And then divide the whole parentheses over. Do that, Caitlin. Okay, all right. Number 5. Find equation of the tangent line. So that means we have to find the derivative, and then evaluate the derivative at the point, get the slope, and then point slope form. Now, we can rewrite this here. Y equals x squared. This is really 5 to the x to the 1/7. And this is in the form of a to the u. So as a reminder, the derivative for a to the u looks a lot like e to the u, just a little bit of adjustment in front. But it's the original function times the exponent's derivative. But we have to go through product rule, and then once we get to that g prime, we can apply this rule. Thank you. Yeah, I'll take it. Thanks. Okay, f prime becomes 2x. G function, no changes. Back to f. Okay, g prime, natural log of 5 times the original function, original term, times u prime. So power rule, x to the 1/7 becomes 1/7 x to the negative 6/7. Okay, we have our derivative. We need to get to the slope. To get to the slope, we're going to evaluate this derivative at 1. So plug 1 in for all the x's. Nice thing is that 1 will wipe out, will just make things a lot cleaner. 2 times 1, 5 to the first power is still 1, so 2 times 5. 1 natural log of 5 times 5 to the 1 times 1/7 times 1. Okay, still a little bit longer than what we expect from slope, but cleaner than before. Okay, so there's our slope. So our point is 1.5. Slope m. So now point slope form. It's a little bit longer than other slopes, but just write all that down. X minus 1. Okay. Number 6. This is basically a variable raised to a variable. The hint is to use log differentiation. Let's rewrite this first. Raised to the x over 3, or 1/3 x. So variable raised to a variable. We don't have a rule for this. We have to find a way to bring that down. So if we introduce natural log into the problem, then power property can allow that 1/3 x to come down. Okay, so now that we're here at this step, there's a little bit of implicit that's going on the left side, but the right side is just product rule. Okay, natural log of y, u prime over u. So 1 over y, but we have to involve dy dx here. F prime g plus fg prime. U prime over u, 2 minus 14x. Okay, not much that we can do with this cleanup, but we are going to move that y over to the right side. And then replace the y back with the original expressions. Good, Caitlin. All right, number 7. Derivative of inverse at a point. I like to go through my chart here. I know that whatever x value they give you is really the y value, because this is the x value of the inverse, which is really the y value of the original. So first thing we do is we want to set that -7 in for the y and solve for the x. Okay, guess and check our way to the x value. Okay, so we try different values here. 1 minus 3 plus 5 plus 9 doesn't equal to 0. But if I did -1, I get -1 minus 3, it's -4. -4 minus 5 is -9. -9 plus 9 is 0. So that works. Okay, so -1 is the key that allows us to move forward. So all we need to do is find f prime of x. And then evaluate the derivative at -1. Derivative power rule. Plug -1 in for x. Three plus 6 plus 5 is 14. So we know that the slope of the f graph is 14, which means that at the corresponding point on the inverse side of things, the slope is related to this number, is the reciprocal of this number. Okay. Any questions? No? Okay.